Welcome back to our discussion of points of local maxima and local minima for a function of two variables. In the previous lecture, we had seen a necessary condition for a function of two variables to have a local maxima and minima at a point. So, we said if a function of two variables has partial derivatives at a point, and if the point is a local point of local maxima or a minima, then both the partial derivatives with respect to the variables x and y should be equal to 0. So, this gave us possible candidates like in one variable where the function can have local maxima or minima. So, the points were the interior points in the domain where the partial derivatives exist and are equal to 0, or either of the partial derivatives does not exist, and the third possibility is the boundary points for the domain. So, we looked at some examples and we saw there were some points which were neither local maxima or local minima, but the partial derivatives were 0 at that point. So, let us that motivated us to look at what is called the saddle points for a function of two variables. So, we will define today what are the saddle points, what are called the saddle points for a function of two variables and analyze them. So, a saddle point is suppose f is a function of two variables from R2 to R, and P is a point in the domain, and let P be a critical point. So, a critical point is an interior point where the derivatives are equal to 0. So, we call P to be a saddle point if for every open ball centered at P, there is a point Q in the and there is a point R in the ball, of course, in the domain such that the value at the point Q is bigger than the value at the point P and is bigger than the value at the point P. That means, every neighborhood of that point P has a point where the value is bigger than the value at P and a point R where the value is smaller than the value at the point P. Such points are called saddle points. For example, let us look at the function f x y equal to x square minus y square, where x and y belong to R2. And for this, if we look at the partial derivatives, they turn out to be 2x and 2y, and when they put them equal to 0, you will get 0, 0 is a critical point. Our claim is that this is a saddle point. To show that, that is obvious actually, because if I take a point close to the origin and where y is 0, so that is a point on the x axis, then the value will be positive. And if I take a point on the y axis, then x will be 0, the value will be minus y square. So, close to 0, we can have points where the value is positive, and also points close to the origin where the value is negative, and the value at 0, 0, the value is 0. So, 0, 0 is a saddle point by the above definition. Let us look at the curve f x function f x y is equal to x y. The domain of the function is the whole of R2, and if I look at for every delta, look at the value of the function at the point delta by 2, then f of x y will be equal to delta square by 4, which is bigger than 0. At the same time, if I look at the value of the function at a point say minus delta by 2 and delta by 2, then the value of the function will be minus delta square by 4, which is less than 0. So, by choosing delta sufficiently close to 0, we see that we can find points close in the domain of the function close to the origin where the values are positive, and another point where the value is negative. So, this means 0, 0 is also a saddle point for this function of two variables f x y equal to x times y. Note that 0, 0 is a saddle point, and if you look at the partial derivatives for this function, the partial derivative with respect to x is equal to y, and the partial derivative with respect to y is equal to x. And so, that means 0, 0 is in fact a critical point. So, 0, 0 is a critical point but it is neither a maximum nor a minimum for the function. So, that means 0, 0 is a critical point and a saddle point. We can also look at some more examples like 2 x square y plus y x square. For this, if I look at the line passing through the origin, the line y equal to x passing through the origin, then the function looks like x is equal to y. So, that is x cube, 2 x cube and x cube, so that is 3 x cube. So, that means close to 0, 0, if it is on the positive side, it will take the positive value, and on the negative, if x negative close to 0, it will take the negative value. So, 0, 0 is a point of is a saddle point for this function. So, this is the way we can analyze saddle points by definition, namely these are the points which are critical points for the function, but the function is neither taking the local maxima or nor is a local minima at that point. In fact, every point for every neighborhood there is a point where the value is bigger and a neighborhood where the value is smaller. So, let us now look at what is called the derivative test for a function of two variables to be having a local maxima or local minima at a point. So, let us take a function of two variables f x y, and let us x naught y naught be an interior point. So, such that both the second order partial derivatives of f at x 0 y 0 exist. Then we define a quantity called the discriminant. It is a 2 by 2 determinant. So, that is defined as this is a notation used for discriminant and defined as 2 by 2 determinant f, where the first row is f x x, the second order partial derivative at x 0 y 0, the f x y, the partial derivative at the point x 0 y 0, and here across is f y x, the partial derivative at x 0 y 0, and f y y at x 0 y 0. In case you have not seen this kind of object earlier, this is just you cross multiply and you write. So, this can also be written as f x x into f y y minus f x y f y y. So, that is the expanded form of this 2 by 2 determinant discriminant. Whether it is called the discriminant is a 2 by 2 determinant. So, the derivative test is in terms of this discriminant, which is something similar to the second order derivative test for a function of one variable. So, let us state this test for the local maxima and local minima for a function of two variables. So, let f be a function of two variables such that all its first and second order partial derivatives exist and are continuous at the point x 0 y 0 in a neighborhood of the point x 0 y 0. This condition basically is put to ensure that the mixed second order partial derivatives are equal. So, that is a sufficient condition. So, we want that the second order partial derivatives exist and are continuous at every point in a neighborhood of the point x 0 y 0, and the first order derivatives are 0. So, that means there is a critical point. So, it is a critical point, the second order partial derivatives exist and our mixed partial derivatives are equal. So, we say that the test says that the function will have a local maximum at the point x 0 y 0 if, so this is a sufficient condition, if the discriminant at that point is bigger than 0 and the partial derivative f x x at that point is less than 0, or equivalently f y y is less than 0. Either of it is enough to ensure. So, these two conditions, that the discriminant is bigger than 0 and the partial derivative x x x, second order partial derivative with respect to x is less than 0, or the partial derivative with respect to y is less than 0. So, these two conditions ensure that the function has a local maximum at the point x 0 y 0. If the discriminant is still bigger than 0, but the partial derivative at the point x x x partial derivative, second order partial derivative at the point x 0 y 0 is bigger than 0, or equivalently the second order partial derivative with respect to y is bigger than 0, then this will ensure that the function has a local minimum at the point x 0 y 0. So, this condition is for sufficient condition for local maximum, and this is a sufficient condition for local minimum. And in case if the discriminant is less than 0, so this was bigger than 0, this is bigger than 0, this is in case the discriminant is less than 0, we can straight away conclude that the function will have a saddle point at the point x 0 y 0. And in case discriminant is equal to 0, no conclusion can be drawn from the conditions of x double derivatives or anything. The function can have a local maximum, function can have a local minimum, and may not have either of it if this condition is satisfied. So, for a sufficiency condition for local maxima or local minima, first the discriminant should be positive, and if the second order derivatives f x x is less than 0, then it is a local maximum. If it is bigger than 0, it is a local minimum. So, these are this is what is called a second order derivative test for local maximum and local minimum. We will see some applications of this, how this is applied. So, let us look at an example. F x y is equal to 4 x y minus x 4 minus y 4. So, this function is has partial derivatives of with respect to x and y at every point. So, let us find out the partial derivatives. When you find the partial derivatives with respect to x, so it will be 4 x, right, with respect to x. So, that will be 4 y minus 4 with respect to x. So, it will be 4 y minus 4 x cube. So, this will be the derivative, partial derivative at the point x 0 y 0. Similarly, when you take the partial derivative with respect to y, so it will be 4 x minus this will be 0 and this will be minus 4 x 4 y cube. So, that will be the partial derivative at the point x 0 y 0. So, to find the critical points, we put them equal to 0, and once you put them equal to 0 and solve these equations, from these two equations, it is easy to see that the solutions are 0 0, 1 1 and minus 1 minus 1. We have not given the details here, but these two equal to 0 and you analyze, because once it is equal to 0, that means y 0 is equal to x cube. Y 0 is equal to x cube, and put the value here and solve, and you will get the required value. So, there are 3 critical points for this function 0 0, 1 1 and minus 1 minus 1. So, let us look at the second order derivatives. The second order partial derivative with respect to x x. So, we will look at this point. So, with respect to x, we want to differentiate, this will give you 0 and this will give you 3. So, minus 3 into 4, that is minus 12 x square, and similarly the other partial derivative f y y at x 0 y 0 we can calculate, and the partial derivative f x y is equal to 4. So, all the 3 partial derivatives are available under the, because we had put those conditions that mixed partial derivatives will be equal once the partial derivatives exist and are continuous. So, this is going to be the case. So, only this is required. So, in the discriminant, the first term will be the partial derivative with respect to x x. So, that is 12 x square. The second term is the partial derivative mixed second order partial derivative, that is equal to 4. So, the first term in the second row is the mixed partial derivative, that is 4 again, and f y y, that is minus 12 y square. So, once you open that, so and cross multiply. So, if you cross multiply, 4 from here is common, 4. So, 3 is common. So, there is 16 from the first row or first column, either one, 4 is common, second also 4 is common. So, 16. So, when you multiply this, this will give you 144 x square y square minus 16. So, 16 out is common. So, 9 x square y square minus 1. So, that is a discriminant, and we have to analyze this discriminant at those critical points which were 0 0 1 1 and minus 1 minus 1. So, at 0 0 the value is minus 16, that is less than 0. So, we can safely conclude that the point 0 0 is a saddle point, because discriminant less than 0 gave you condition. Sufficiency condition was that this should be a saddle point. So, now let us look at the discriminant for the value 1 1. When it is 1 1, it is going to be positive. So, it is 128. So, the same value at the point minus 1, because it is x naught square y naught square. So, it does not matter whether it is positive or negative. So, at 1 1 or minus 1 1, both the points, the value of the discriminant is 128, which is bigger than 0. So, now let us analyze what is the value of f x x at the point 1 1, and similarly at the point minus 1, which when you put the value in this, at when you put is 1, that is minus 12, when you put it 1, that is minus 1. So, it is square. So, either way it does not matter. So, whether plus 1 or minus 1, the value of the second order derivative is at 1 1, and minus 1 are negative less than 0. So, that means what? That means the points 1 1 and minus 1 are points of local maximum, because the discriminant at these points is bigger than 0 and the second order partial derivatives are less than 0. So, these points are local maximum. So, both the points 1 1 and minus 1 are points of local maximum and for the function. We have already concluded 0 0 is a saddle point, but you can also analyze it by definition along the line y equal to x, f x x is always bigger than 0, and along the line x is equal to minus y, the function f y y f x minus y is less than 0. So, as close as you want near 0 0, you can have a positive value at a point and a negative value at 0 0, the value being 0. So, the function has a saddle point at the point 0 0. So, one can also analyze more examples like the function f x y equal to minus x 4 y 4. First order partial derivatives are equal to 0, and for this, because it will give first order partial derivative will give you 4 x cube, this will give you 4 y cube, put equal to 0, 0 0 is a critical point, and you calculate the second order partial derivatives, they are all 0. So, discriminant is also equal to 0. So, discriminant is 0. So, second derivative test is inconclusive. For this case, we cannot apply it. However, if you look at the function at 0 0, the value is 0, at every other point the value is negative. So, 0 0 is going to be a point of local maximum for this function, though the test fails. Similarly, if I invert the function, change the sign here as x 4 plus y 4, all this will remain the same. The function will have a local minimum at the point 0 0, because in that case f at 0 0 is 0, but f at every other point will have a positive value. So, the idea of this example is that when the discriminant is 0, and even if the point is a critical point, it may be a local maxima, it may be a local minima, as just now exhibited. So, finally, let us look at another example of this function 4 x cube y minus 4 x y cube, and calculate the partial derivatives, and they come out to be 0. Discriminant comes out to be equal to 0, but at this the point 0 0 is a point of is a saddle point, which we can verify as follows. Look at the values of the function along the curve t and comma t minus t by 2. If I look, so that means x is equal to t and y is equal to minus t by 2. So, this is a curve going through 0 0, and along this the value of the function is minus 74 by 4, which will be negative for all points close to 0 0. And similarly, if we change t to t by 2, the curve is x 1 t is equal to t and y 1 t equal to t by 2. So, along this curve which is passing through 0 0, the value of the function is 7 t by 4 by 4. So, it will be positive. So, very close to 0 0 the function takes both the values positive and negative values. So, 0 0 is a saddle point for this function and the test fails. So, these examples illustrate that the test may fail, but still the function may have a local maxima, may have a local minima or a saddle point at the point where the test is failing. So, these examples illustrate those only conditions are sufficient only when the discriminant is bigger than 0. Like one variable, we can also look at functions of two variables and define what is called an absolute maxima or an absolute minima of the function in the domain. So, f is a function defined in a domain R2 to R, a point in the domain a vector A, a point A in the domain D is called a point of absolute maxima if f of A is bigger than or equal to f of x y for all x y in the domain. So, it is a global property. For all values in the domain, f of A is the value which is the largest. So, this is called absolute maxima, and the point A is called the point of absolute maxima. And similarly, you can define absolute minima to be the point B in the domain such that f of x y, the value of the function at every other point, is bigger than or equal to the value of the function at that point. So, that point is called the absolute point of absolute minima, and the value is called the absolute minima for the function, going parallel to functions of one variable. And again, going parallel to the function of one variable, recall that if a function is defined in a closed bounded interval for one variable, the absolute maxima and the absolute minima exist, and same property is true for functions of two variables. So, what are the points where absolute maxima can occur? So, clearly a function is defined in a domain D in R2. So, if a function has a absolute maximum at a point A, so then the point A either is a boundary point or is a critical point for the function. So, that means what? Either A should be a critical point or A is a boundary point. So, critical point meant that either it is an interior point where the both partial order derivative, first order partial derivatives are equal to 0, or the points where either of the partial derivatives does not, at least one of the partial derivatives does not exist. Similarly, for absolute minima. So, that means to find out the possible candidates where a function of two variables can have absolute maxima or absolute minima are the points, the boundary points or the critical points. So, to locate, analyze a function and find its point of absolute maxima and absolute minima, what one does is look at the function, find out its critical points, find out the boundary points and analyze the values of the function at these points. Perfectly similar to one variable situation. Some examples, let us observe. As I said, we find out the critical points, we found out the boundary points, find out the values and compare. Okay. So, let us analyze, let us one example. So, domain of the function is given, that is x y in R2, mod x less than 2, mod y less than 2. That means, it is a square in the plane centered at 0 0 with length x going up to 2 and on this side minus 2. So, the four corners are given by 2 0, minus 2 0, and similarly at the top it will be right. So, centered at the origin, going up 2 units, going down 2 units. So, that is the square and here is the origin. So, that is that. So, the function given to us is 4 x y minus 2 y square minus y 4. So, we want to find out the absolute maximum of this function in this domain. So, this domain has interior and as well as boundary. The interior is when mod x is strictly less than 2 and mod y is strictly less than 2. So, that is inside of the square, and the boundary of the square is the normal boundary of the square, where mod x is equal to 2, mod y is equal to 2. So, let us analyze that. So, it is a continuous function. So, it will have absolute maximum and absolute minimum. And to find out that, let us look at the partial derivatives. So, these are the partial derivatives of the function of two variables, and when you put them equal to 0, that gives you 0 0 1 0 1 1 and minus 1 minus 1. So, that fourth point is not visible here. So, that is, so we need to compare the values at these points. So, and the boundary points. On a boundary point, x is equal to 2 or x is equal to minus 2 or y equal to 2 and y equal to minus 2. So, when we put that values in the function, so and function is symmetric with respect to x and y. So, we need to determine the absolute minimum and absolute minimum of the function. We have to only find out f of 2 y. So, that is a boundary point when x is equal to 2, that vertical line is given by this, and y goes between minus 2 to 2. So, it is a function of one variable, and similarly for x 2 when y is equal to 2. So, that is a vertical line at the top, and x is varying between minus 2 to 2. So, for a function of one variable, we can analyze the conditions for this to be equal to 0 and find out absolute minimum. So, one can check, we will leave it for you to check that as a function of one variable in y, it has a absolute maximum at the point y equal to cube root of 2, and similarly f 2 y has a absolute maximum at the point y is equal to cube root of 2. So, and the minimum at the point y equal to minus 2. So, this is a function of one variable, analysis will give you these values. So, now we can compare all the values of the function at all the points. F 0 0 is 0, f 1 1 is 1, f 2 cube root of 2 is equal to minus 40, f 2 2 is equal to. So, at all the points, boundary points and the critical points, find the values and compare. So, you see that f of and also we have ignored the points minus 1 and minus 2 because of symmetry. So, we can include that also. So, that means absolute maximum of f is 1, and at the point 1 1 and minus 1 minus 1, and similarly it has a absolute minimum is minus 40 at the point 2 minus 2 minus 2 minus 2. So, this is how you analyze absolute maximum and absolute minimum of functions of two variables. We will see some example of this in our economics model also. Thank you.